Okay, anyone else need it? Cool, okay. So I'll close this up. No, okay, they want to close it up that way. Let me just see. Okay. So I'm back to my tablet. So glad to have you all here. Welcome. And what problems would you like to go over or see done? So I've got my review sheet near me, so I'm expecting probably some problems from that list, but it could be anything actually. So request.
Can we do problem
Yeah.
10 on page 75?
Okay, so I got a couple people talking there, but I think I heard problem 10 on page 75. Is that what I heard?
Yeah, that's correct.
Okay. Any other requests?
Can we go over the proof for theorem 1.8?
Proof of 1.8. What page is that on? Is it 44? Okay. Any other requests? If we could get a list, that would be great. Then we can see which ones people want to see most and go from there.
Can we get 10 on page 35?
Sure. Problem 10 on page 35. Okay.
I do page 19, or sorry, number 19 on page 22.
Problem 19 on 22.
Yes.
Okay. Okay, looks like a fine list. We can do a few more if you got it, or we can just start doing these either way.
If it's not too much to ask, can I record?
Oh, no problem at all.
I got here a little late, my bad.
Yeah, that's fine. I just have to, it's not a problem. Let me just see if I can get to that place. Okay, so I am a place, and who's requesting it? I'm sorry.
James,
James. There you are. Okay,
thank you, Professor.
no problem. Anyone else need it? Okay, so let me go back to sharing. All right, and we,
Sir,
yeah,
are you going to be going over these problems on how you expect to see them at the test, on the test?
yeah, pretty much, except sometimes I may not be writing down everything, but you should, between what I write and what I say is probably what you should, try to do on the test, yes. Any others? Well, why don't we vote on these?
Professor, could you
Yeah.
could you go over number 8, page 55?
Let me write down.
You don't have to do like the whole problem, just like how do we approach that kind of problem? Does it have like a lot of vectors and stuff?
Okay, so again, it was problem which?
Number 8, page 55.
55, okay. Well, why don't you all look at these problems? There's 5 of them. And decide which ones, you want to really see, which ones you want to see first. So I'll give you another, 10 seconds to do that. Look them all over. They're, throughout the whole front of the book. And let me just call it problem 10 on page 75. Theorem 1.8 on page 44, problem 10 on page 35, problem 19 on page 22, problem 8 on on page 55. Okay, so you could vote for as many of these as you want to see. You can vote for all of them or for none of them, it's up to you. So let me start with problem 10 on page 75. Raise your hand or give some gesture if you want to see that problem. Problem 10 on page 75. So far, I see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 votes for that. Okay, please take your hands down. Next, let's decide. Juan, you still have your hand up. Okay. Let's see how many want theorem 1.8 on page 44. How many want me to go over that proof? Theorem 1.8 on page 44. Raise your hands again if you want that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So roughly 10, 11. So almost the same count. I'm wondering if that's how it's going to be for all of these. Okay, please put your hands down, your gestures down. Thank you. How many are interested in problem 10 on page 35? Page 35, problem 10. 1, 2, 3, 4, 5, 6, 7, maybe. Yeah, 7.
Professor,
Uh-huh.
I think someone said that they're having trouble raising their reactions. I think it was Alberto.
Okay.
He said in
Well,
the comments.
okay. No offense, one vote here or there won't matter. Okay, okay, so don't worry about it too much here. But continue to try. Yeah, I don't know. There's somewhere there's a reaction button there. Let's just keep going. Problem 19 on page 22. So if you can raise your hand or give me some reaction, please do it for problem 19, page 22. So far I see 1, 2, 3, 4, 5, 6, 7, and 7 is all I see. Okay, and then finally, last one, problem 8. You can lower your hands. Problem 8 on page 55. Problem 8 on page 55. Please give me a reaction of some sort if you're interested in that one. So I see 1, 2, 3, 4. So that's not a very big, okay, good. So it's pretty much in the order that people asked. So let's do number 10 on 75 first and go from there. Thank you for giving me an indication. So we're trying to do the high demand ones first, right? So let's go back to this screen and let me move this out of the way. Move some of the other stuff out of the way. Good. Okay. And let me see. Huh. Well, let's see if this is going to let me scroll down. Oh, I see. A little bit, but I need a little more room than that. Okay, so now we're getting some room. So we're looking at number 10 on page 75. So that's more recent. So let's take a look at that. So number 10 says, suppose, let me put some glasses on here so I can read. Suppose T is going from R2 to R2. So for this one, T is going from R2 to R2. And it's linear. That part is fine. And T of 1, 0 is 1, 4. And T of 1, 1 is equal to 2, 5. What is T of 2, 3? and is T1 to 1. Okay, so fair enough. Let me see, I can't, as soon as I put the book away, I gotta make sure one thing pulled out. Yeah, so this to me looked like a negative sign there. Okay. So first thing I think I would do, well, you could notice that 1, 0 and 1, 1. That's actually a basis in R2. What does that mean? Well, it means that together it spans the whole space and that the vectors themselves are linearly independent of each other. I don't think it would be hard to see that. In fact, you could even 1, 0 is this vector here, and 1, 1 is this vector here. And I think you can see that together you can get any vector you want out of that. But let's assume that for the moment, that that's a basis. And the illustration that I would like to use is that something times this one, A1 times 1, 0, plus some constant times this one, would be equal to 2, 3. Since I think it's the basis, I should be able to get any vector in R2. And in particular, I should be able to get 2, 3. Well, if that's going to happen, then if we look at the first coefficients, it would say that A1 times 1 plus A2 times 1 would have to be equal to 2. And it would also say the second components, A1 times 0, which is 0, and A2 times 1, which again is A2, would have to be equal to 3. So from these two equations, you already have, this one tells you that A2 is 3. And if this is 3, 3 plus -1 would be this. So that means A1 is -1. Let's just verify it. So if I put in -1 in here, and if I put in 3 in here, does it work? -1 plus 3 is 2, and 3 times 1 is that. Okay, so we do have 2, 3 as a linear combination of these two. And the reason I did that is because they asked me for T of this. So what I would say now is T of 2, 3 would be the same as T of this stuff. -1 times 1, 0 plus 3 times 1, 1. Because we just saw, well, maybe I need an extra pair of parentheses here. No. We just saw that 2, 3 is equal to that linear combination. So, but T is linear, so what does that mean? That means this is equal to -1 times T of 1, 0 plus 3 times T of 1, 1. And both of these were given. So T of 1, 0 is 1, 4. I can put this in for 1, 4 in for that, times -1. plus 3, and t of 1, 1 was what, 2, 5? 2, 5. Okay. And so that should be the answer. So what is it? It looks like -1 from here plus 6, so that would be 5. And then -4 from here plus 15, so that would be 11. So that's my answer for the first part of it. T2, 3 should be this, 511. Any questions about that part? Okay, so did I do this right? 6 minus 1, yes. 15 minus, yeah, that's that. So the answer to this one is 5/11. 5,11. Okay, now the next question is T1 to 1. Well, there's different ways to answer that, but one way that we just did the other day in class comes to mind. T is 1 to 1 if and only if and only if the null space is just the 0 vector. In this case, there's no confusion about what 0 vector we're talking about because we're going from R2 to R2. So the only 0 vector in town is this one. Okay, so we know, so if we know the null space is just this, then we know it's 1 to 1. Perhaps another way to say it is so maybe the easiest way to do this is to say the following. So we know this. We know the nullity plus the rank is equal to the dimension of R2, which is just 2. So this is the dimension theorem. So one way to show the nullity is the dimension of this, to show that that's 0, which is what we're trying to show. We're trying to think it's 1 to 1, is to see that the rank is 2. So one way to find the rank of such a transformation is we can use theorem 2.2. Let me make sure I'm referring to the right theorem. So it's in that section. Yeah, it's on page 68. And theorem 2.2 says if you have a linear transformation and you know what the basis is, then you can find the span of that basis. Well, let me just say what it says. Okay, so look at theorem 2.2. It's on page 68. So we need to look at that. Page 68. What does it say? It says that you have a transformation going from some vector space V into some vector space W, and assume that these are vector spaces and assume that T is linear. And if you have a basis of V, so in this case, well, in this case, I think we have a basis of V because I already said I think this is a basis. So if a basis of V, in this case, I can think of it as 1, 0, and what, 1, 1. That's a basis of V, and V is R2 in this case. Then what the theorem says, if you take T of this set, which would be what happens if you take T of 1, 0, and T of 1, 1. So take T of each of these. And what are those numbers? We know those because those were given. T of 1, 0 is 1, 4. So this is 1, 4. And T of 1, 1 is 2, 5. Okay, so what the theorem says, this spans the range. Okay, now we already know that the range is a subset of R2. And it looks to me that this is a basis. How do I know that's a basis? Well, first of all, these vectors are linearly independent. How do I know that? Well, there's only two of them. If they weren't linearly independent, then one would just be a multiple of the other. Well, if I'm trying to get this one from this one, if I multiply by 2, I would get 2, 8, which is not this one. So I can see that these are going to be independent. Is it clear that they span, well, it spans RT, and they're independent. So what I'm suggesting is, let me just say it. I'm saying this is a basis. So T of B is just R2, which means in this dimension result, this is 2, which means this is 0. Because 0 plus 2 has to be 2 by the dimension theorem. So the nullity has dimension 0, which means this is the only thing in it. Okay. The dimension of a single 0 vector is just 0. So that means, yes, it's 1 to 1. Yes, T is 1 to 1. Now, that's a rather long way to do this problem, but I think it's correct.
How did you think the rank was?
Well, I knew the rank was 2 because this is a basis for, the theorem tells me T of beta is a basis, or actually it tells me this spans RT. That's the conclusion. So every linear combination of this is what's in RT. But I could see that this itself are independent. And since they span this would be a basis for RT. So that means RT is two-dimensional because there's two vectors in this basis. So basically, I know this thing is a basis this is a basis of RT. How do I know that? The theorem tells me it spans RT, and I could see that they were also independent. So together, spanning and being independent means it's the basis, which means it's the dimension of RT is 2. Now that's one way to do it, but I think there's probably an easier way. Before talking about an easier way, does everyone understand what I did here? I sort of used a couple of results. I used theorem 2.2 to get this spanning set of RT, and then I noticed that they were independent. So that meant this is a basis of RT. That means RT is two-dimensional, and then I used the dimension theorem. I know this is 2, I know this is 2, so that has to be 0. And that means the nullity is 0, and that means it's 1 to 1. Let's see if there's an easier way to do this. But for the moment, any questions on this way? Okay, so I think an easier way to do this would be, let me see, maybe we can just show it directly without all these theorems. So let's see if we take so suppose T of X is the zero vector. So that means X would be what? An element of the null space. If we can show that X is only the 0, 0 vector, that would be great. Then that would show the null space as only the 0 vector in it. And then we have that previous result that I've already talked about, that T is 1 to 1 if and only if the null space only consists of the 0 vector. So let's try to show that the only vectors that go to 0 is the 0 vector. Well, all right, any vector, we have a basis here of R2. So any vector, let's say that X has components X1 and X2. Okay. And we know that X can be written as something in the basis. We already said that this is the basis of R2. So let's say it's something times, maybe I don't want to say this, components X1, X2. I just want to say that X is a vector that goes to 0. And then in terms of the basis, it would be something like A1 times what? 1, 1 or 1, 0 rather. Plus A2 times the other base factor, which is 1, 1. Okay, so X could be written as a linear combination of these. So what would T of X, suppose we take T of X. So T of X on one hand would be A1 T of 1, 0 plus A2 T of 1, 1. That's because T is linear. So when it works on a sum, you do the T of each of them, and these constants would be taken outside. A1 and A2 are constants, they're real numbers. Okay. But on the other hand, we know what these things are. That was given. So T of 1, 0 is 1, 4. So this is A1, 1, comma 4. And T of 1, 1 was given to be originally 2, 5, right? So this is information that was given at the beginning. Okay. And we're assuming that T of X is going to the 0 vector. So this all has to be equal to what? 0, 0? Well, okay, now you could just equate the coefficients. So this would be A1, 1, A1 times 1, which is just A1, plus 2 times A2. That would have to be equal to 0. And 4 times A1 plus 5 times A2 would also have to be equal to 0. So we're assuming that X is something in the null space, which means T of X is 0, 0. So this is the alternate argument, even though we've done it one way. I'm trying to show a different way here. Okay, so can we say what A1 and A2 have to be? Well, sure. So from this one, A1 would be minus 2A2, just bring this to the other side. And if you substitute this into here, you'd have 4A1, but A1 is now minus 2A, 2. And plus 5A2, and that's equal to 0. So what do you have? Minus 8a2 plus 5a2, which is what? Minus 3a2. And if that equals 0, that implies a2 is 0. And if a2 is 0, that implies a1 is 0. So we're sort of done because we started with any vector that's a linear combination of this, and we assume that t is sent to 0. And if t is sent to 0, if x is sent to 0 rather by t, then it turns out that a1 and a2 are the same. So the only vector that gets sent to 0 is the 0 vector, and that's enough to show that it's one-to-one directly by this earlier result. So maybe that's a little more elementary. You understand either of the two ways. You don't have to understand both, but it might be nice if you did. But do you understand at least one of the two ways? Any questions?
Would another way to be like maybe taking a not taking a guess, but like thinking about what the transformation is actually doing, like coming up with what the transformation is, I guess.
Yeah, that would be yet another way. In fact, yes, that would work. Well, coming up with the transformation, then you have a general rule for the transformation, right? And then maybe you could use a modified version of what I just did with that transformation to see what vectors go to 0. Or maybe you can use the first way where you can figure out the nullity and the rank. So yeah, you could find the co-transformation. In fact, let me see if we got it. I think we sort of have it, right? Let's just pursue that just one more step. I mean, this is an unusual problem at this point. Sometimes we struggle to find one way to do it.
Yeah, I mean, I had an idea of what it is just by looking at what was given.
Sure, go with it. What's your idea?
It was the first, so for x1, the first component plus the second component. So yeah, comma 4x1 plus x2.
Okay, so you're telling me this is what you think t is about. I think that's what you're telling me.
Yeah, that's what I meant. Yeah, sorry.
No, that's fine. Hang on one second. I've got a phone ringing. I just want to make sure it's not important. I'll be right back. Okay, sorry it got delayed. I actually have a little problem, but it's something I can take care of. So let's see, we're trying to look at this problem yet another way. And I forgot who the student was. I'm sorry, who was helping me with this?
That was Seth.
Hey, Seth, yeah. So you think the transformation is doing this, right?
Yeah, I'm pretty sure it is.
Yeah, well, the easiest way to check is just the 2 points we had. So does it agree with that? If you put in 1, 0, 1, 0, do you get 1, 4? And I think that's right. And if you put in 1, 1, do you get 2, 5? 1, 1, 2, 5. Yeah, it looks good. Okay. Yeah, so if you already have this as being a transformation, you can just say, when is this equal to the 0 vector? And for it to be equal to the 0 vector, x1 plus x2 would have to be 0. And for x1 plus x2 would have to be 0. But this is very similar to what we just did up here, because x1, x2 would be minus x1. So putting that in here, you get 3x1 is 0, which implies x1 is 0. And if x1 is 0, that implies x2 is 0. So the only vector that goes to the 0 vector is the 0 vector, and that means it's 1 to 1. So yeah, if you already know, so there's a third way, which is maybe faster than the other ways, although somebody could say, how do you know this? And so yeah, I guess I could even say that. So if you gave me this on the test, my question would be, how do I know this? I don't know what your answer would be.
That's a good question.
Okay, so when you put down, when you have to solve it on a test, you need to justify, your steps. I think you're correct. And I think it would give you a quick answer to the second part of the question. It probably give you a quick answer to the first part of the question too, which was to find what.
Yeah, it does. It works for that as well. Yeah.
So I think it all comes down to, how do you know this is what the transformation is doing?
Intuition.
Yeah. Well, you could tighten it up, because I think you could do what I did, sort of what I did over here. Let's see if this is giving me the same thing.
Yeah, that
Okay.
method looks better, honestly, I would say.
Yeah, let me look at it a little more. Yeah, it would take me a little while, but I think you could probably use this idea. Yeah, what I would think I would do. Let me see. Yeah, I think maybe this would be the answer to that question. Because, okay, you want to know what t of x does, and suppose x just looks like let me see. Yeah, okay, so it'd be a little bit more. Okay, so here's a way to tighten up what you're saying. X is equal to this. So really what it comes down to, if you think of x as x1 comma x2, then it would have to be equal to a1 this would be a1 1. What do we want? A's here. Let me see. Okay. So this really means x1 times 1, 0 plus x2 times what? 0, 1. And that's a different basis than this one. Okay. So I think you'd want this one. So yeah, so here's what you would do with this one. You would take this expression here and d of x1 comma x2. I'd first write x1 comma x2 in terms of the basis you have. So that would be A110 plus A211. And then this is the same vector, just written in different basis. So I would figure out what A1 is. So X1 here would have to be A1 plus A2. And X2 here would be what? Nothing from here and just A2. So what does that say? It says that A2 has to be X2. And then it has to be what? A1 would have to be X1 minus X2. So any vector X1, X2 would be written as A1, which is X1 minus X2 times 10 plus A2, which is X2. 1. Okay, let's make sure this actually works. So X1 would be equal to X1 minus X2 plus X2. That's correct. And then the second component here, X2, would be 0 from here and just this. So this is correct. So any vector in the usual basis would be written this way in this basis. And then you could do what? T of this would be X1 minus X2 T of this plus X2 T of this. And then put in the values that you know from this, because those were given, right? Where from the beginning up here. So if you put those in, T10 is 1,4. This one is 1,4. And the other one I forgot.
2.5.
What is it?
It's 2.5.
2,5, thank you. 2,5. And then if you expand all this out, you would have this times 1 plus this times 2. So that looks like X1 plus X2, right? If you look at the first component, X1 minus X2 times 1 plus X2 times 2. So it's just X1 plus X2. And then the next one would be what? 0 from here, and you would just get X2. Is that what your transformation was? No. So I messed it up somewhere here. You guessed the transformation to be this, right? So maybe I'm messing it up here at the end. Oh yeah, it should be this times, I did it times 0, it should be that times 4, my bad. So the second component should be 4x1 minus 4x2 from this, plus what? 5x2. And if you add that up, what do you get? You get, let me make sure I'm doing this right. 4 times this, that's right. And x2 times 2, 5. And just the fifth one here, right? So that would be 4x1 plus x2. That's what you got. Okay. So I did derive you're correct. Your formula is right. And I derived it. I don't know if this made some sense to you. Did it make some sense to what I'm doing?
Yeah, I've seen it.
Got it. So that's what you'd have to add. But even if you didn't say that, if this all turns out to be right, you'd still get a lot of credit for this. The only thing you get docked on is, why is this true? Unless you have some kind of answer. Anyway, we've done this problem 3 ways. That's probably more than enough. Let's move on. What's next? Oh, it's the proof 1.8 from page 44. So let's just turn the page, I think.
Somebody in the chat asked how many questions are going to be on the test.
I don't know. Okay. No, I don't even have a sample test to help you. When someone asked me that in my other class, at least I had a sample test. And so my other class, which is a different class at all, it was 7 out of 9. But I mean, maybe something like that. I don't know. I haven't made up the test yet. So I honestly don't know. Okay. But if I had to answer, maybe 7 out of 9 is as good an answer as anything. But now what are we doing? Theorem 1.8 on page 44. So let me see what that's about. So that's further back. So let's see what it says. But before I go through it, is that one of the theorems that I asked you to know by heart? Let me make sure. Yep, it's on the list, so that's good. Okay, so let's look at it. It says, so hopefully you have it in front of you too, so I don't have to rewrite it all. Let V be a vector space, let U1 to UN be a distinct vectors in there. Beta is a basis if and only if each V can be uniquely expressed as a linear combination of vectors in beta. That is, if it can be expressed in a form like this, where this is unique. Okay, so let's write. So if this were on the test, you should write, you probably would say state improve. So let's at least state what I have here. Let V be a vector space. Okay. And what else? And vectors U1 to UN be distinct vectors in there. And vectors U1, U2, U3, all the way up to UN. Be distinct. Distinct is important. That means they're not the same. Distinct vectors in B. So I'll underline distinct because that's an important adjective there. Then here comes the conclusion. Then if you take all these vectors and put them in a set, U1, U2, UN, then this is a basis if and only if each vector in V can be uniquely expressed as a linear combination of vectors of beta. Beta is this collection. That is, it can be expressed in the form. That says that is. V can be expressed as A1, U1 plus A2, U2, all the way up to AN, UN. for unique another keyword, scalars. A1, A2, all the way up to AN. Okay, so that's the full statement of the thing. It's rather lengthy, but all right, let's just go through the proof that's in the book, because I think that's probably the proof I did in class. Let me see if I can move some of this stuff out of the way. Maybe not. Okay. So proof. So first assume beta is the basis. So this is an if and only if, right? So this is beta as a basis is part of what we're either assuming or proving. And that's true if and only if every vector in V can be written this way with unique scalars A1 to AN. So they start off by assuming this part. So the proof is going in this direction. We get to assume this way that beta is a basis of what? Of V. Okay. And if little v is any vector, then V is in the span of beta. So if you have a vector little v in capital V, the vector space, then little v is in the span of beta. Why? Well, that's any vector. If this is a basis, we know that every vector in V can be written as a linear combination of base vectors. So that's really all this is saying. So put another way, you get to write, we know you can write, so V can be expressed just sort of in the way they want here. V is a linear combination of vectors of beta. Okay. So, okay. So the only thing, so in a way you're sort of done. Okay, so V can be written this way. We know it can be written this way for A1 up to AN in, say, the reals or whatever it is here. Scalars. I think they're real numbers anyway. And that follows because if beta is a basis, then any vector in here can be written this way. And all they're trying to show is that this can be done uniquely. So what they're going to say is, suppose this could be done in two different ways, and then they're going to show you that there's only one way. So we already know it could be done in one way. Suppose it can be done in another way, and the other way they put in what? B's. B1, U1, plus B2, U2, all the way to what? Bn, Un. Remember that U1 up to UN is a basis. And so we're saying, suppose it could be described in two ways, where these are scalars as well. Then what they want to see, or what they want to prove, want to show, that that A1 equals B1 and A2 equals B2 all the way up the line. AN equals BN. Because that means it can be done this way in a unique fashion. Okay, so in order to show that, what they simply do is subtract the second equation from the first. Since they're both equal to V, you can just think of these two equations and just subtract this one from the first. V minus V would be the zero vector. But these line up, so this would be what? A1 minus B1 times U1, and A2 minus B2 times U2, all the way down to the end of the line, AN minus BN times UN. Okay, so that means the zero vector is written as a linear combination of these U's. But since U's are a basis, we also know, since we're assuming that beta is a basis, this implies the vectors in there are, the U's are what? Linearly independent. Why? Because in a basis, all the vectors are linearly independent and they span the whole space. Well, if they're linearly independent, when you have a linear combination of this to sort equal to zero, that would mean each of the coefficients are zero. So the linearly independence implies,
All the A's minus all the B's equals 0.
well, we're almost there. We're getting A1 minus B1 equals 0. And A2 equals B2, or A2 minus B2 must be 0. Why? Because that's our definition of linear independent. Vectors are linear independent. If you put them in a combination like this, then all the coefficients are 0 until you get to the end of the line. AN minus BN equals 0. But this is the same as saying that A1 is B1. And this is the same as saying that A2 is B2. Let's put the second term. Wow, if I could write, it would help. This is B2, doesn't even look like it. A2 equals B2, and in general, AN equals BN. And that means they're unique. There's only one way to do it, because we assumed that there were two ways to do it, one with A's and one with B's. And by subtracting one equation to the other, we got this equation, which we know has only one solution. Each of these parenthetical coefficients must be 0. But that means that all the A's are equal individually to all the B's. So that means we've shown that this could equal this only one way. You can't have two different ways to express this, because we were able to show that if you had two ways, they're really the same. Okay, that's half the proof. That's the proof assuming that beta is a basis, right? So if beta is a basis, then this can be written this way in a unique way. Any questions about the first half of the proof? Okay, now we got to turn the reasoning around. So for the second half, the converse is left as an exercise. Okay, so they don't do the other way around. Let's see if we can do it. So what did I intend you to know? I actually intended you, I didn't realize the converse wasn't even done here. Let's see how hard the converse is, because they don't even do it in the book. So they just did this direction. Let's try the converse. So the converse would be the opposite direction. So what do you get to assume? Go back up here. You get to assume that you have distinct vectors U1 to UN, and you get to assume that every vector in V can be written this way for unique scalars like this. So we get to assume this way, we get to assume that we have U1, U2, UN, and We're assuming those are distinct vectors in V. What does that mean? No two of them are the same. So they're all different than each other. And we're also assuming that any vector in V can be written as a linear combination of these guys. So we also get to assume for any little v and big V, little v can be written as A1 U1 plus A2 U2 all up to the last one, AN UN. So any vector in little v and capital V can be written this way. And we get to assume that the A's are unique. Can be written this way, where A1, A2, all the way up to AN are unique scalars. Okay. So that's true. That's what we're assuming, that we have a collection of U's that are distinct, and that for any little v and capital V, we can write them in this way where the A's are unique. Now, what is it we're trying to show? We're trying to show that the collection beta, which is U1, U2, all the way up to UN, is a basis, right? Before we assumed we had a basis and we showed all this, now we're doing the other way. We're assuming all this and we're trying to show that this would be a basis. Well, okay. To show it's a basis, what do we have to show? We have, by definition, we need to see that beta is what? Linearly independent. And beta spans V. Okay, those are the two conditions to be a basis. But the second condition is pretty much immediate. Why? Because any vector in V can be written as a linear combination of the U's. Well, that's what spanning means. If every vector in the whole space can be written as a linear combination of the U's, then and betas are in our, and the U's are in our beta, that's this condition. So that's sort of immediate from what we're assuming. So the only thing to worry about is, are the U's linearly independent? And what you do for that one is you set, so this is true. And for this one, we just set V here equal to the zero vector in V. Okay. So if we do that, then the zero vector in V can also be written as a linear combination of these. For some A's. And it can only be written in that way in a unique manner. But I'm claiming I know what the A's are. But I claim A1 equals 0, equal A2, equal A3, all the way down the line until you get to the last guy. So if you set them all equal to 0, then what would you get on the right? Well, 0 times any vector, this is all just going to be the 0 vector. And the 0 vector equals the 0 vector. So certainly this is one solution to this. But the A's are unique. So there's only one way to do this. So the only solution to this is this one. So first of all, it's obvious that this is a solution because if you pick all the A's to be zero, then you have the zero vector on both sides of the equation, and that's true. The zero vector equals the zero vector. But to show they're linearly independent, what you really need to show is that there's no other solution other than the zeros. But then this thing is telling you that the only solution, they are unique scalars. So if this is a solution, any other solution would have to be the same of it. So that means there is no other solution of A's other than this one. So what does that mean? That shows it's linearly independent and you're done. Let me do the last half again, because I'm not sure we ever do the last. I'm not sure we'd ever do that in class. Probably I left it to as an exercise. So in this case, we're assuming that these vectors you use are distinct in V and that any linear combination of them, that for any vector in V, you can write it as a linear combination of these guys. And you can do that in a way such that the coefficients are unique. So there's only one way to do it. Okay, so assuming that condition, we're trying to show that the collection of the U's is a basis. To be a basis, there are two properties. Beta has to be linearly independent and beta has to span V. Spanning V is almost immediate because this says any vector in here can be written as a linear combination of the U's. That's what spanning V is all about. So spanning V is immediate from this condition. What's not immediate is that beta is linearly independent. For the vectors in here to be linearly independent, it means whenever you have a linear combination of them set equal to the zero vector, the only solution is this. Hang on a second. You're good. Thank you. Okay, so I'm sorry, I lost my track there. So if you set this equal to the zero vector, we're trying to show that the only solution of this equation is the one where they're all zeros. What is all zeros? All the A's. Well, certainly if you pick all the A's to be zeros, that will work because 0 times any vector is 0. And you're adding up a whole bunch of zero vectors, and on the right side, you just get the zero vector, which means you get equality, which is true. So this is definitely one solution, but now you have to argue it's the only solution, but you don't have to worry about it because they said there are only unique constants that make this thing work. So that means if you found one solution, that's the only solution there is. That's what unique constant scalars mean. So that means it's linearly independent, and together with the spanning, that means it's a basis. Questions on this? It's sort of a good problem for understanding what it means to be a basis. Any questions? The first half of the proof is pretty much straight out of the book, and the second half is an exercise, but it's pretty easy. Okay, so let me move along. What next? Problem 10, page 35. Okay. So I'm looking to see where that fits on our study sheet. Problem 10. There is no problem 10 on the proofs to know list. Problem 10, page 35 is on the sample problems. Okay, so that's good. It's one of the sample problems. Let's turn to it. Any questions on this slide before I flip away? Okay, so let's turn away from it, add a page, put some lines on here, enlarge it, and let's go to problem 10 on page 35. Problem 10 on page 35. I don't remember the problem at all, so let's look at it. Page 35, number 10. Okay, so it says, show that if M1, M2, and M3 are these 2x2 matrices, then the span of M1, M2, and M3 is the set of all symmetric and 2x2 matrices. Okay. So let me write it down. Show that if matrix 1 looks like this, 1 in this position, 0 in these three positions. Matrix 2 looks like this. And matrix 3 looks like this. So if these 3 2x2 matrices look like that, then the span of M1, M2, M3 equals all matrices that are 2x2 and symmetric. I don't remember if they have a special symbol for symmetry. Let me go back and see if we do. But this probably was defined way back someplace in the big matrices. So where do they tell you what a symmetric matrix is? I'm just going to look in the back for it under the index. So I'm looking up symmetric matrix. So you'll see it, so let me look up matrices. Matrices.
It's on page 18.
Oh, thank you. Yeah, I'm just curious now that I'm here. Yeah, and the index would have led me there. Thank you. So 18. So yeah, it's like the third paragraph on 18. A symmetric matrix is one so that the transpose is equal to itself. Clearly, a symmetric matrix must be squared. Let W be the set of all symmetric matrices. So they don't give it a special name. Okay. I thought they might. So I think they just say symmetric matrices in this guy, in the 2x2s. All right, but let me just tell you what it looks like. A matrix, a 2x2 matrix, normally a 2x2 matrix would just have 4 entries, A, B, C, D. Or if you like, A11, A12, A21, A22. Those are general matrices. But to be symmetric, if you transpose it, you get the same thing. Or let me just tell you what it means. To be symmetric means that Aij equals Aji for all I and j. Well, that doesn't say much when I and j are the same. A11 equals A11. That's not too meaningful. But it does mean more here. It says that A12 is A21. So it means these two guys are the same. And then on the diagonal, it doesn't mean too much. Okay. So symmetric matrices look like what? If I were to rewrite this one, if this is B, then I don't need to call this C. I would call this B as well. And then I can call this C. So this would be what a symmetric 2x2 matrix looks like. And if I wanted to use this notation, A12 is the same as A21, so I can just call this A12 again if you wish, and keep this notation. So for 2x2 matrices, if you just want to think of it as letters, there's three letters and off this is called the main diagonal, off the main diagonal, these would be the same. But this definition is maybe a little more general because it would work not only for a 2 by 2, but n by n. So what does it mean? It means whenever you have an n by n matrix, the diagonals look like this, 2, 2, all the way down to ANN. Somewhere over here sits at AIJ, and somewhere over here would be AJI. And these are the same. Or if you want to think of reflecting this in the diagonal like a mirror, then it, on the other side would appear the same number. Okay, well, that's it more generally, but this problem here is only dealing with 2 by 2. So why don't we think of 2 by 2 matrices that are symmetric as looking like this? We don't need all this terminology, I don't think. Any question about what symmetric means? We need to know what symmetric means to even prove this, right? So I'm going to erase, well, okay, I won't erase it, but I'll put it, I don't think you need this stuff. That's more general. I think the takeaway is just, this is how a symmetric 2 by 2 matrix looks. This is a symmetric 2 by 2 matrix. So, it turns out if you take all symmetric 2 by 2 matrices, they are subspace. It's not immediately obvious. And they're not actually even asking you to prove that. What they're asking you to prove is that the span of these guys will give you all 2 by 2 symmetric matrices. So I think you can see how that's going to work now. What does the span of these guys look like? It would look like A1 times M1 plus A2 times M2 plus A3 times M3. The span of any set of vectors, or in this case matrices, is just a linear combination of them, where the A's are what? Coefficients, A1, A2, A3 are scalars, usually numbers in the reals. Okay, so we're trying to show that if we take the span of these three guys, you could get any symmetric matrix, 2 by 2 symmetric matrix, so A, B, B, C. Well, I think if you put in what these are, it'll become pretty clear how to do this. So A11, this one was what, 1, 0, 0, 0, I believe. Got to go back and make sure, yep. And M2 was 0, 0, 0, 1. And M3 was the one that had what? 2 1s in it here. So we're trying to show that any matrix of this form where A, B, and C are also real numbers can be gotten by picking A1 and A2 and A3 appropriately. So what would be appropriately? Just equate the coefficients. The upper left-hand entry here would be obtained by A1. So let's just write it down. It would be obtained by A1 times 1 plus A2 times 0, which is 0, plus A3 times 0, which is 0. So we've just deduced that A1 is really A. And now let's go to the next entry, B. B on the left would have to be A1 times 0, which is nothing, A2 times 0, which is still nothing, and A3 times 1, which is just A3. So this is the same as saying that B would have to be A3. So we're figuring out what A1 and A2 would have to be. So far we have this. If we do the next entry down here, it's not going to get us anything new. It would say B would be equal to A1 times 0, which is gone, and A2 times 0, which is nothing, and A3 times this. So it gives us the same equality that we had over here, so it's not exciting. But the last, equating the last entry, the lower right-hand corner entry would give us C is equal to A1 times 0, which is zip, A2 times 1, which is A2, and A3 times 0, which is 0. So this tells us C is equal to A2. Okay, so the boxed equations are what we're after. Let's just put in what it says. It says make A1 equal to A. Make A2 equal to C. And make A3 equal to B. So I think we're done. We can just check that it works. What we're checking is that this linear combination of these three matrices, M1, M2, and M3, would get you any 2x2 symmetric matrix. Well, you can see why, because this times A would just put an A in this corner, and this times B would put B's in these two places, and C times this would just put a C in the lower right-hand corner. And if you add them up, you're just going to have the A in this place, the C here, and the two B's there. That's pretty much what the problem is about. Questions?
So the M3 matrix was already a symmetric matrix, huh?
That's correct. Well, actually, all of them were. To be symmetric, you only need to have A1, 2, and these two to be the same, and they are.
Oh,
Yeah.
that's right. Yeah.
No condition for the diagonal, but yeah, all three, M1, M2, and M3 were all symmetric. And what we've shown is that this this spans this. So here's the question that, okay, we're done, I think. Let me look at the book. I think that was the whole question. Where was this? I forgot. Page 35 or something. Yeah. Then the span is this. Okay. If a normal question that comes to mind is you've just shown that these three vectors span the symmetric matrices. Now, the next question would be, is M1, M2, M3 a basis?
Yes.
Yeah, but what would you have to show? You'd have to show that M1, M2, and M3 are linearly independent. We've just shown they span all the symmetric matrices. But to be a basis, you have to span and be linearly independent. So what you would have to show next, if I can be a little lazy here, you'd have to show that the only solution to this,
Matrix of zeros.
yeah, the only solution to this equation would be A1, A2, and A3 being zeros. But I think you could see where that would be true because, again, just equate the coefficients, right? So that means this is not only a spanning set, it's also a basis. So anyway, that was too natural to ask for me to pass up. Okay, any questions on this? So we're getting progress, making progress. We've got 3 down and 2 to go. One is way back on page 22, so I don't know what that is. Let me flip the page.
It's one of the theorems that you told us.
Yeah, that makes sense. So any question on this before I flip it? This thing at the end was just a natural afterthought. Okay, let's flip it. Add a new page, put some lines on, and now let's go off in search of problem 19.
Or it's not a theorem, but it's a proof.
Page 22. Oh yeah, that's on our proofs to know. Okay, so yeah, that's more theoretical probably. Let's go back and look at that. Ah. Page 22. Oh, yeah. No. Oh, page, problem 19. Got it. Let W1, W2 be subspaces of the vector space. Prove that the union is a subspace if and only if W1 is contained in W2 or the other way around. Oh, God, yeah, we did that, but do I remember? Not offhand. Let me see. So let's write it out. Maybe you feel the same way. Did you find it in your notes, out of curiosity? Because I know we proved it, we did it in class, by the way. So W1 and W2 are subspaces let W1 and W2 be subspaces of the vector space capital V. Prove that W1 union W2 is a subspace of V if and only if and only if W1 is contained in W2 or W2 is contained in W1. Okay. Oh, this is like a fresh one for me because it's been too long ago. I haven't looked at it for a while. So which one is easier? I think it's easier. Yeah. So this is an if and only if. I usually try to do the easy one first. By the way, if there's an easy problem, if there's a way to do the first part of a problem, if you know the easy way, go for it. It's partial credit and it may give you ideas on the other way. So I'm a believer in trying to make some results, try to get something before you try the hardest part. So for me, I think the easy part is going this way. So it's an if and only if, so we have two directions to go. I will go this direction. So what does that mean? I get to assume this. Suppose, so for all of it, we get to assume this. W1 and W2 are subspaces of V. That's an overreaching assumption. And so I'm going to assume I'm going to suppose W1 is either a subset of W2 or W2 is a subset of W1. And I'm checking one thing. I always get confused with the subset notation. Is it, do I have it right? Yeah. So okay, so think of it this way. This is cases. Case one, W1 is a subset of W2. So how does the picture look? We know that these are both subspaces of V. So think of V as the big space, the Venn diagram. And W1 is a subset of W2. That's the case we're in. So the bigger set could be thought of as W2. And the smaller set could be thought of as W1. Okay, so that's the Venn diagram. Now notice if this is true, then W1 union W2. Well, if you take the union of a smaller set with the bigger set, you just get the bigger set, right? Because if you're in one or the other or both, that would just be the bigger set, right? So notice if W1 is a subset of W2, then this union is W2. And W2 is a subspace to begin with. So since this is a subspace, that means this is a subspace. So that's not too hard on argument. Let's make sure it makes sense. I'm going in the backward direction. I'm assuming that either W1 is a subset of W2 or W2 is a subset of W1. And I guess I should remind ourselves that W1 and W2 are more than just subsets, they're subspaces. Okay, so that is known throughout this one. So if the picture looks like this, which is the first case, then I claim the union would just be the bigger of the two sets. So the union would be W2, and we're trying to show that W1 union W2 is a subspace. Well, it automatically is. Why? Because it's equal to W2, and W2 was given to be a subspace. So we're done. And maybe I should write that. This is a subspace since W1 union W2 equals W2, and this is known to be a subspace, to be a subspace. And since this is a subspace and this equals this, that means it's a subspace. Are there any questions about that argument? Okay, good, because the other case 2 is almost identical, right? Case 2, maybe this one doesn't hold, maybe this one holds. But if this one holds, then the picture looks like this. The whole vector space is there. The bigger one this time is W1. And the subset of that is W2. So the picture looks similar. But this W2 is the smaller one. So this is the case when W2 is a subset of W1. So there's the or. But in that case, if you take their union, you're just going to get the bigger of the two sets, which is W1. So whenever you union two things together, you get everything that's in one or the other or both. And if one is bigger than the other one, then you get everything in the bigger one. Bigger meaning that which has the other as a subset. So then it's still true. So the union here is equal to W1. This is a subspace. By assumption. You ask me where it's assumed that. I will direct you up here to the underlying thing. W1 and W2 are subspaces of V. So since this is a subspace, and since this equals this, that means, and therefore, W1 union W2 is also is a subspace. So, okay. If this seems a little easy, I think it's the easy direction, okay? I think this one is the easy way. But in terms of the number of points, if this were like 25 points, this would be like 12 or 13 points, half the problem you got if you do these two cases. Any questions about this direction?
On the test, would pictures be a good way to show that like we understand what's going on there for you?
Sure, can't hurt. Yes. Yes, pictures, words. You can't say it out loud, so write it down, right? I can say it out loud here. So for me, it's a little trickier because it's tempting just to say things out loud and not write it out in a long sentence. But if I were doing the test, most of what I've been saying out loud, I would write down. So words and pictures are fine.
I was thinking of like defining W1 and W2, but the picture seems like a quicker way to do it.
Yeah, well, I mean, if this were really, somebody was really rigorous, I suppose somebody could say, why is this? Okay. And that's a 310 kind of argument, not 3100 rather. Okay. So, I mean, okay, I don't want to do this, but you make me think of it at least. In the first case, one could say, why is this equality true? So what you would have to show is you'd have to show two things. If you were to do this as a 3100 kind of argument, which I'm not asking you to do, but just getting into the you would have to show that this is a subset of that, and then you'd have to show that this is a subset of that. And in math 3100, that's how you show two sets are equal. And maybe I'll just do one, but I really don't want you doing this, okay? But you bring up the picture. So somebody who's thinking about 3100, we try to avoid proofs by picture, right? So then how would you actually show this argument? Let's just show this one. The other should be similar. So all I have to do is show that something in here is in here. So I pick something that's, let's call it, hopefully it's okay if I call it omega. Omega is in W1 or union W2. And what does that mean? This means omega is either in W1 or, that's what union means, omega is in W2. If omega is in W2, then automatically it's on the right side and you're done. If omega is in W1, then omega will be in W2. Why? Because you're assuming in this case that W1 is a subset of that, which means everything that's an element of this is an element of that. So even if you're just in W1, then you're automatically in W2 because we're working on the assumption case one. In either case, if omega was in W1 or in omega 2, in either case, you're able to show that this union is contained in W2, the bigger of the two sets. Okay, now, I can do this. Do I want you to do that? Not particularly. I'd be more pleased, to be honest, if you showed me these pictures.
That's perfect.
Okay?
That's actually a relief.
Yeah, no, that's, I mean, yeah, I'm not looking for this level of rigor. There's different levels of rigor, and I'm happy to use the pictures in these cases. They're very suggestive and they're very helpful. But for those who were, who really maybe had somebody teaching 3100 who said, oh, you can't use these pictures, you got to make an argument based just on the logic. Look, I understand that kind of stuff, and you should be able to do it, but that's not really what I'm teaching in this class. So that's why I'm not looking for this. If you do this and don't give me the pictures and you do this right, will you get full credit? Sure. If you do this and don't show me the pictures and mess this up, then you'll probably lose some points. Okay. So anyway, all these different possibilities are there. I would recommend the pictures. Now, what about the other direction? The other direction, I think, is the harder direction. But so the other direction is let's do that one. That's this way. So what do we get to assume and what do we have to show? So we're always assuming in both cases that W1 and W2 are subspaces of V. So that's an overriding assumption. But now we assume that the union is a subspace. So now assume W1 union W2 is what? Is a subspace of V. And show the only way that could happen. So then show or prove that W1 either has to be a subset of W2 or the other way around, right? Okay, so this time we get to assume that the union is a subspace, and we're trying to show W1 is a subset of W2 or the other way around. So we're trying to show that the picture's got to look like one of these two. Okay. So if the picture doesn't look like one of these two, then what must it look like? Well, okay, we've got two sets. Let's do the picture again, the Venn diagram. I think it's the way to go. Here's the whole vector space.
Are you thinking of a contradiction approach?
Maybe, yeah. Yeah, let's think. I'm thinking that I know what the union generally looks like. The union looks like there's three different real cases here. The union could look like this, where W1 and W2 have nothing in common at all. The union could look like this, where they have something in common and it's just what's in both sets. Or it could be what we've already shown, that one is a subset of the other. So it could be like this, for example, or the other way around. So if you have two sets, then the union is one of these three, right? It's either the case where there is nothing in common, or it's the case where one is a subset of the other, either this or the reverse. What I mean by that, either this or this one. The bigger one is W2 and this is W1. Or it looks like this. And what I'd like to do is eliminate these two as possible. So if knowing this is a subspace, I'd like to argue that these two can't happen. And if these two can happen, then it has to be one of these two, okay? So that's sort of the argument that I hope will work. So let's see if we can eliminate this guy. If this happens, then they're disjoint. That can't happen. Why? Because then the union would just be, well, okay, why can't this happen? Both sets have to have something in common. What? The zero vector. Remember, these are subspaces, right? So they're not just subsets, they're subspaces. And every subspace has to have the zero vector in it. Remember, the whole Venn diagram is V, right? The vector space. So I'm claiming this can't happen because it's impossible to have the zero vector of V in here and the zero vector of V in here. And yet that would have to be the case. If you have the zero vector in this one, since this has nothing in common with that, then this would not have the zero vector in here, right? The zero vector can't be in both. It has to be in both of these sets, but it can't be because these sets are disjoint. Okay, so the argument would be, if this is how the V1, W1 and W2 looks like, then let's make sure that's right. Oh, I guess that's, no, maybe I'm not off on that. Let's think about that. Yeah, they both have to have, okay, so this means this picture can't happen because they both have to have zero V. I said it right the first time. Zero V has to be in both sets, but there is nothing that's in both. There is no element that's in both sets. Why? From the picture. The picture tells you that W1 intersection W2 is empty, right? And yet they both have to have the zero vector in there because they're subspaces. So what does that mean? This is out by contradiction. Okay, so now we just have to show that this can't happen. If this happens, what goes wrong? Well, what does that mean? That means there has to be something over here.
My guess is we wouldn't have closure probably.
Yeah, I think so too. Let's see what it would mean. I'm trying to see, yeah. So if this is how the picture looks, there has to be an element over here called W1. W1 is a particular omega 1 or something. Let me make this look bigger. Let me draw my picture again. Maybe I should use X and Y. That would be easier. Okay, so if this is W1 and this is W2, and the picture looks like this, then there has to be something over here, a vector, call it X, and there has to be a vector over here, Y. Yeah. And I think your idea of closure is a good thing to look for, right? Because if you had, so there has to be something that's just in, so what does this say? Say that X would be a member of W1 and X would what? Not be a member of W2? Yeah, you're outside the W2, you're in the complement. And similarly, Y would be a member of W2, and what would happen? Y is not a member of W1. Okay, so there'd have to be some vectors that look like that. And I think your idea is good. What happens if you add these two guys together? Well, if you add them together, and we're also assuming we're assuming that the union is not only the union, it's also a subspace. So since this is in one and this is in the other, the union would have to be in W1 union W2, right? Yeah, because X being in W1 implies what? X is in W1 union W2. And Y being in W2 implies Y is in W1 union W2. So X and Y are in this union, and that would mean that X plus Y is in the union. And let's think about that. Where could it be? Well, it has to be in one of these guys, right? So suppose there's two cases. Case one, suppose X plus Y is in W1. Okay, but what does that mean? Well, if X plus Y is in W1, and we already knew that X was in W1. So if you subtract this from this, you'll get Y is in W1. Why? Because again, it's closed. If this is in W1 and this is in W1, and W1 is a subspace, their difference would still be in there. That means Y is in W1. But we already said Y is not in W1. So that's a contradiction. So then, okay, so there's only one other case left. The other case would be what? Case two. Maybe X plus Y is not in, it's got to be one or the other. So if it's not in W1, it would be in W2. Because you know that, this is in a union, okay. But what do you know now? You know X plus Y is in W2. And you also know Y is in W2. And so if you take the difference, you'll get X plus Y minus Y, which would be X, and that would also have to be in W2 by closure. But we already knew that X was not in W2 way up here. So that's also a contradiction. Yeah, so you asked, is it going to be a proof by contradiction? I guess so. I didn't really think about it at that time so much. So let me play this last one part again. I'm trying to say that it's in no way can I have the picture look like this and the union of the two subspaces be the union of the two subsets be a subspace. Because if it does look like this, then there would be an X that's in W1 and not in W2. I put it over here, and there'd be an element over here that's in W2 and not in W1. So there'd be an X and Y that look like that. But then the question occurs, where does their sum live? Well, since X is in W1 and Y is in W2, both of these are elements of this union. And since the union is assumed to be a subspace, and by the way, this should be written down. Okay. Let me say it. Let me write it. Since this is true, since X is an element of W1, and what? Y is an element of W2, then X is also an element of W1 union W2. If you're in W1, you're automatically in the union, and Y would also be an element of W1